When we're dealing with exponential growth and decay, one is picking the right formula. Most of the equations you work with deal with exponential growth, because when you get to savings account, investment accounts, anything like that, those are all exponential growth. The only decay we usually look at is radioactive decay. We will also often look at decay on the amount of medicine that is left in your system after you first take it. So those kind of things is usually where they're at. So population growth or population decay. So most of these formulas are very similar to each other. It's not something that you will have to memorize even for the test. At this point, you will just need to make sure that you know how to use them. You know what the variables represent. And where to put all the pieces. So with these, in this first section, is it growth or is it decay? So a certain town has a current population of 32,500 with a 1.25% annual rate of growth. When will the population reach 50,000? So the first thing you want to do is label everything they gave you. So they gave us the present population. They gave us what we want to check the future population to be. And they gave us the rate, but we need to write it as a decimal. So anytime you have a percent rate, whether it's growth or decay, you always change those out to decimals. So those are the only pieces they gave us. We know it is an annual growth rate. So that means the number of compounds is just 1. So we're going to check this rate, say, at the end of every year. I always start by writing the formula that I'm going to use. Because then I very clearly can see exactly where all the pieces need to go once I've labeled them. So that means the future population of 50,000, the initial population of 32,500, 1 plus 0.0125, and t over 1. Because it's an annual growth rate, we're only measuring it once a year. So we need to know when we are solving for t. I need to isolate this base that has the exponent on it. So that means I'm going to start by dividing both sides by 32,500. Does it come out to be a nice decimal value? So we don't really get a nice solid decimal number, do we? Okay, so then what I want to do is I want to leave it, if you put it in your calculator, you can simplify it. Just right here, you could go on ahead and just knock off those extra zeros. You want the answer to be as accurate as possible. which means you're going to keep the answer pieces rolling until you get to the final answer. Since I need to solve for the exponent, and there's no way to get these bases the same, we rewrite it as a logarithm. So t equals log base 1.0125 of this 500 over 325. You can go ahead and leave it as 50,000 over 32,500. But again, just knock off my extra zeros. Don't have to worry about it as much. All right, now we go to the work we did in the last lesson. Rewrite it as a common logarithm. So that is going to be the log of the fraction over the log of 1.0125. What did you end up with on that?
34.68.
And then you just tack on a unit, whatever they're measuring this in, they're measuring it in years. So almost about 34 and a half years for that to take place. Going ahead, unless told otherwise, most everything is rounded to the hundredths. All your money is going to be rounded to the nearest cent. So that's 2 decimal places. So just keep it consistent. Round everything to 2 decimal places. If you're not told. Okay? So anytime you have to get to the exponent and find that particular answer, rewriting it as a logarithm. That's going to be the way you want to go with that. All right. So we have a current population of about 14,378. The population has an annual growth rate of 1.96%. What will the population be after 3 years? So again, labeling everything we have. We have the current population. We have the rate as a decimal. Annual rate of growth means n is 1. And this time, they gave us the time. We're dealing with growth. So the first thing I'm going to do is write the formula so I can more easily see where all the pieces are going. I have the current population plus the interest rate. And I want to know what it's going to be in 3 years. So the only variable is the new population, and it's already over here by itself. There's no variables over here where all the work is. So at this point, I'm just going to do the math of this problem. And I get 15,240 point. What'd you get?
1-1.
1-1. Okay. So the question is, do we measure population as parts of people? No. So that's the other thing to watch, is we're going to take that decimal off and round it. If you're dealing in number of years, if you're dealing in money, then that's fine to have your decimal. If you're dealing in number of people, those would be your situations that. Why did you drop it?
I just did.
Oh.
I got like 15.2.
So, based on the situation, you may be dropping your decimal altogether and just the nearest whole number. Okay. All right. Solve this one. When are we going to get to 20,000 people? This will be like number 1, where you're solving for the years. All right. So the equation, again, we're dealing with growth. So we want to know when it reaches 20,000. It's already 14,378. We have the rate of growth. And annual interest rate. So this one, again, you're still going to, we're trying to get find t. So we have to isolate this area that has that base. Dividing both sides by this 14,378. Dividing it, but not actually doing the division yet. Because I want to keep the answer rolling and as accurate as possible, so I do not round to the very end. So I have 20,000 over 14,378 equals 1.0196 to t. To get at that variable, rewrite it as your logarithm. So t equals log base 1.0196 of the 20,000 over the 14,378. Then rewrite it as a common logarithm.
So you don't have to simplify the fraction.
No, you can completely leave it as it is. So I leave it like that because I'm not actually going to do anything in my calculator until I have it to that point, written as a common logarithm. And it's going to take us approximately 17.00 years. So approximately 17 years. So you with the both 2 zeros on the end like that, you can leave it there, you can take them off. So about 17 years. All right, decreasing population. Same thing, except this time we're going to subtract our rate. Keep in mind, This decimal is a percent, so we're still going to have to move the decimal two places when we go to write this. So we've got our new population. We've got the original population. And 1 minus the interest rate or the rate of decay. T over 1. Again, the fact that it's an annual rate tells us that that n is 1. Well, do the same thing we did before. Do the division to isolate that base. Over 319,365. And then 1 minus that decimal. Okay, so 0.9976. So we need to get to that exponents, rewrite it as a logarithm. That'll be your next step. And when you rewrite it as a logarithm, then we'll rewrite as a common log to actually do the work. So that step, even though it may seem tedious to do that and then rewrite it, is to make sure you get everything in the correct place. Because too many times when students skip this first step as a logarithm and go directly to the common log, they have things backwards. Okay. All right, so common log. And then over 319,365 over the log of that lovely decimal. So in the calculator, watch what you are putting into the calculator. Most of you have the 2-line calculator, so always a good idea to double check your work. And we get approximately 5.02 years. So even though that decrease doesn't seem like a lot, we're talking about a big city like that, in 5 years, they're going to lose about 4,000 people if that rate continues. And depending on the neighborhood that it's coming from, if it's all coming from one neighborhood, that could be a really big problem for the businesses in that particular neighborhood. So city planners continually watch these kind of statistics and this information. Okay. Same thing. We've got a decreasing rate of 5.2% this time. When will the population drop from 50,000 to 40,000? So setup will be the exact same. So another decay. So making sure we set it up with the correct formula. The new population is 40,000. The initial population is 50,000. 1 minus the interest rate and T over 1. Because again, that per year means that they're checking the rate, checking it yearly on that then. So, divide by the 50,000. So we end up with 40,000 over 50,000. And then we have our rates and 0.948 to the T. Now the nice thing with this one is 40,000 over 50,000 is just 0.844 fifths. So it's a nice decimal. You can leave it, you can put it like that. You can rewrite it as 4/5 instead. Any of that's fine, since it's a terminating decimal. Well, we need to find that exponent. So the only option, rewrite it as a logarithm. Log of base 0.948 to the 0.8. Then the common logarithm means it's the log of 0.8 divided by the log of your base. So we get approximately 4.18 years. So not very long. Because again, losing the number of people means you're losing that tax base that they paid. Then that also means the businesses are not getting as many customers, so your businesses may look to relocate. So there's a lot of fallout when cities start seeing a population decrease. All right, money. Very, very important. Something we want to keep in mind. There's several ways to compound. The first one we're going to take a look at is just compounded at a specific time within the year. So you have the breakout of annually, semi-annually, quarterly, monthly, weekly. It's a very similar formula to population growth, except you're going to divide the rate by the number of compounds that happen in that year. So, first thing we do, we know the formula we're using. So identifying all of our pieces. So if 1,200 is invested in a savings account, so that's how much we initially put in. It's compounded quarterly. So N is 4. Our rate is still changed to a decimal. How long will it take the account to reach 3,000? So then we are going to plug that into all of the pieces. So again, that formula. When we're dealing with money, then the number of times it's compounded times the year. So there's a few more pieces to this one. All right, place it all. So 3,000 equals 1200. 1 plus 0.0425 divided by 4. And then your exponent is 4t. So then we can go about dividing both sides by that 1200. This gives us a nice decimal. So it gives us 2.5, which I can work from. Simplifying all of this in the parentheses. So 1 plus 425 divided by 4. 1.01065 to the t. Do not round anything until the very end.
What happened to the 4?
I did 1 plus the 0.0425 divided by 4. So I just did all of that in the calculator.
Yeah, but what happened to the 4 by the t?
Oh, whoops. Yes. That one does still need to be there. Thank you. All right. So now we've got everything condensed in the base. We've isolated it. Rewrite it as a logarithm. So 4t equals log base 1.01065 to the 2.5. So we're going to figure this the same way, except before we're done, we will divide it by 4. So as a common logarithm, I'm going to do that math, then divide both sides, that answer by 4. So the log of 2.5 divided by the log of 1.010625. Divide that answer by 4. And I get approximately 21.67 years. So when you are dealing with accounts like this with compounding interest, you have to take into account and divide by the number of times it's compounded in that year. Okay. Questions on that one? Again, once you set up one, all these problems are pretty much worked the exact same way. All right. So this one, if $3,500 is invested in a savings account that is compounded semi-annually at a rate per year, how long will it take till the account doubles? Well, we have our initial investment. Semi-annually is how many? We have our interest rate. And what is the final amount in this case? 7,000. Okay, set it up, find it. All right, so setting it up. 7,000 equals 3,500. 1 plus 0.0137 over 2 to the 2t. So when I divide by 3,500, I end up with 2. 1.00685 to the 2t. Rewrite that as a log. So then your common log is the log of 2 divided by the log of 1.0. Yep. And then we'll divide that whole answer by 2. And t is approximately 50.77 years. So being watchful when you round, when you don't. Again, usually you'll just want to keep that value going in your calculator and always using that previous answer. All right, 8. So we have the initial amount, compounded monthly at rate of that, and t is 25. So if they ever give you the number of years, know that you're going to have every single piece of the problem and just have to come up with your final answer. So A equals 5,000. 1 plus divided by 12. And then on our exponent, 12 times 25. Now again, what we're figuring is we're assuming they set up this account and they don't add any more money to it. So your calculators, if you are careful with the work, can handle all of this. But you just have to be very careful with your parentheses. Or take it in pieces. What? Did you do the exponent 12 times 25? Did you put that in parentheses when you did it? So then it multiplied the whole thing by 25 instead of as an exponent. So you want to be very, very watchful.
This is people.
So what it's doing is it's only taking it to the 12 exponent and not the 25. Put parentheses around the 12 and 25 and I'll do it. All right, so most of you are getting everything good in your calculator until this exponent piece. If you just do this, it's only taking it to the 12th power and then multiplying your entire answer by 25. So you want parentheses around that.
What if you put parentheses around both of them?
Mm-mm.
At one part?
So the answer is not a lot of money. $5,665.59. So with only 0.5% in interest rate, that's probably not an account you want to put your money in. If you want to earn more money than that. So just being very careful, taking it a piece at a time if you need to, watching where you put those parentheses. All right, so the last part deals with continuously compounding interest, which is usually what banks are measuring your interest rate on. There's fewer pieces of these equations, which is nice. It works with base E and natural log for that. So you still have an initial deposit, $5,000, compounded continuously. When you see that word right there, you know that we are using the base E version of our compounding. So we have our rate. And that's all we need. We have T is 5 years. So we have A, E to the R times T. So 5,000 E to the 0.071 times 5. So there's nothing to solve for. All we need to do is the math of that equation. Now, to get to base E on your calculator, it should be a second function of the natural log button on most of them. So this is approximately $7,130.90. So with that interest rate in 5 years, that's a pretty good deal. Again,
So E is like the natural log.
it isn't the natural log, it's the inverse of it. So you still have to do E to that power.
So you just stack it right there.
Yeah. And it already created the parentheses for you, so you should be good. All right. This is actually an easier one to work with because there's fewer pieces. So see what you can do to set up number 10. If they're wanting the number of years, then you have to isolate the base, which is base E, then rewrite as a logarithm. This time it'll be natural log. You look at this last one. Okie dokie, initial deposits. Rates, 0.012. We want when it's 1,000. So we have 1,000 equals 720 E to the 0.012 T. We still have to isolate the base, which means dividing both sides by 720. If you want, you can take off a 0 or just leave it the way it is. The nice thing with natural logarithms is when you rewrite this as a log, there's no change of base you have to worry about. It just goes directly to 0.012 T equals the natural log of that. So we'll figure out what the natural log is of that, divide it by our decimal over here, and get about 27.38 years. Yes?